All right, so let's transition into talking about the derivatives of the trigonometric functions. And unfortunately, even though we have all of these differentiation rules, none of them are going to apply immediately to the trig functions. But we will be able to apply them once we take the derivative or figure out what the derivative of sine and cosine are. And so our first goal is just to take the derivative of sine theta. So what is the derivative of sine theta? Here's the question. And now we don't have any choice here except to use the limit definition of the derivative. So if I try to find from the definition the derivative of sine theta, okay, so I'm just writing the function here, sine theta, putting the prime to mean derivative with respect to theta, then what do we have? It should be the limit is h goes to 0 of sine theta plus h, so I go just a little bit away from theta, and then subtract sine theta, and then divide by h. Okay, so it looks like we're stuck here, right? Because if we try to just evaluate or plug in h equals 0, we're going to get 0 over 0 in indeterminate form. So we need to do more work. We need to manipulate this expression that we're taking the limit. But this expression involves trigonometric functions. And so how can I rewrite trigonometric functions in a way where things will hopefully simplify? Well, I need to actually use a trig identity. And the trig identity I'm going to use is on this sine theta plus h. I'm actually going to use the angle addition formula. So recall that sine of alpha plus beta is equal to, the way I remember it, it's sine of alpha cosine beta plus, and then you just switch them. So sine alpha cosine beta plus cosine alpha sine beta. Okay, so that's at least going to get us to rewrite this sine of theta plus h, which is kind of the complicated part of this expression. So what do we have? The limit is h goes to 0. Now we can rewrite this as sine theta cosine h plus cosine theta sine h minus sine theta. And then all of this is divided by h. Alrighty. So now things are looking a little bit better because I see at least I can factor out from two of the terms a factor of sine theta. Okay, I don't know where that's going to get me, but I don't have anything else to do. So let me actually group this term and this term together, and then we'll leave that term on its own. So here we'll have the limit is h goes to 0. I can factor out a sine theta. And what am I left with? Cosine of h minus 1. All over h. Plus the limit is h goes to 0 of cosine theta times, okay, so I'm looking at this term here. So I'm going to write it as cosine theta and then times sine h over h. And you'll see why I'm doing that. Because if you look at this limit here, I'm taking the limit as h goes to 0 of sine h over h. But that's a limit that we know. This is going to 1. as h goes to 0. So actually, this second term, second limit that we're taking here, is just cosine of theta times 1, or cosine theta. So this is just cosine theta. But that leaves us with this first limit. So we have this factor of sine theta that doesn't depend on h. And so we're trying to take the limit as h goes to 0 of cosine of h minus 1 over h. Now if we just let h go to 0, that is still an indeterminate form, because we get cosine of 0, which is 1, so 1 minus 1, which is 0 over 0. So we have to do some pretty heavy manipulation here. Okay, so the first thing I'm going to do is multiply by the conjugate, cosine of h plus 1, on the top and bottom. So here and here. And what that's going to do is the top's going to be a difference of squares. So we have the limit as h goes to 0. We have the sine theta. And then we have cosine of h squared, so cosine squared h minus 1, over h times cosine of h plus 1. And again, that comes from, it's a little messy. That comes from just multiplying cosine of h minus 1 times cosine of h plus 1. Alrighty. But here I'm going to use another trig identity. So cosine squared h plus sine squared h is 1. So if I rearrange, cosine squared of h minus 1 is actually equal to minus sine squared h. Again, that's coming from the fact that sine squared h plus cosine squared h is 1. And I'm just rearranging that, manipulating it. Okay, so this is plus cosine theta. So this limit I can write as, so of course this is plus cosine theta. So I can write this as sine theta, and then I can write this as minus sine squared, the h, and then all over h, like that, times cosine of h plus 1. But as h goes to 0, actually we can evaluate this part. So as h goes to 0, cosine of h plus 1 goes to 2. So we actually just get a factor of 2 here, but that's not going to make a difference. The point is, okay, so plus cosine theta, that if I take the limit here, so I can factor out this minus sine theta over 2, and I'm taking the limit as h goes to 0 of sine h times sine h over h. And of course we still have this plus cosine theta. And we're almost done, I promise. But what I want to notice is, okay, so I'm just writing sine squared h over h is sine h times sine h over h. Because as h goes to 0, we know what happens to this. This goes to 1. But as h goes to 0, what happens to sine h? This is going to 0. So actually this entire term is going to 0. But then what are we left with? Just this factor of cosine theta. So the derivative of sine theta is cosine theta. Okay, so we've done a lot of work here. So we've found that the derivative of sine theta is cosine theta. Now we can show by almost an identical argument to what we just did that the derivative of cosine theta is, well, what would you expect? If the derivative of sine theta is cosine theta, you might expect the derivative of cosine theta to be related to sine theta. And it is. It's actually minus sine theta. So for reasons that we'll see when we actually work it out in the examples, we get a negative sign, okay? And that's great. So we know the derivative of sine and cosine. But recall that the rest of the trigonometric functions are defined as either products or quotients of sine and cosine. So let's think for a second. How could we figure out the rest of the derivatives of the trig functions? Let's think about tangent theta. Well, here's the key idea. What is tangent theta? Tangent theta is just sine theta divided by cosine theta. So I can actually just apply the quotient rule because tangent is a quotient of sine and cosine. And I know what the derivative of sine and cosine are. Okay, so what does the quotient rule say? It's low, so the bottom function, times the derivative of the top function, which is cosine theta, and then minus the top function, high, times the derivative of the bottom, d low, which is negative sine theta, all divided by the bottom function squared, so cosine squared theta. But look at this. What's the numerator? This is cosine squared theta. This is going to be minus sine squared theta, but I'm subtracting it, so it's actually plus sine squared theta. The two negatives become a positive. All over cosine squared theta. But what's cosine squared theta plus sine squared theta? This is 1 over cosine squared theta. And if we wanted to be really neat, we actually have a name for 1 over cosine theta. It's secant theta. So this is actually just secant squared theta. So the derivative of tangent is secant squared theta. And notice the beauty of it is that we found the derivative of tangent by just knowing the derivative of sine and cosine. This is a fact that we've highlighted about trig functions again and again, that once we start understanding just sine and cosine, the rest are just combining sine and cosine in a special way. So the same is true about the derivative. And we can do similar techniques with the rest of the trig functions. We just write them in terms of sine and cosine and use the appropriate differentiation rule. So here's a really brief table of the derivatives of the trig functions. Okay, so you can look over that. Now we actually did all the work to justify why the derivative of sine is cosine. I told you that taking the derivative of cosine and showing that it's negative sine is very similar. We'll actually do that in an example. And then tangent, we just use the fact that tangent theta is sine over cosine and use the quotient rule. And we can do the same thing for secant and cosecant. I think we'll do secant in the examples. But if you're thinking about memorizing this table, there's a very useful observation. And I'll see if you can catch it. So the observation is that these derivatives are kind of related. They look very similar. So sine is cosine, cosine is minus sine. Tangent is secant squared, which is 1 over cosine squared. Cotangent is negative cosecant squared, which is negative 1 over sine squared. Secant is secant theta tan theta. Cosecant is negative cosecant theta cotangent theta. So there's definitely some symmetry going on, but the key thing to remember, you say, okay, well, when do I pick up a negative? How can I remember that the derivative of sine is positive cosine while the derivative of cosine is negative sine? Well, here's the observation that's going to really help you out in remembering that. If it starts with a C, pick up a negative. So I'm sure you made that observation looking at this table, that if the function you're taking the derivative of starts with the letter C, then you pick up a negative when you take the derivative. Whereas if it does not start with a C, this top row, you don't have a negative. So that's a little bit silly, but these are the types of things that will actually help you remember the derivative of the trig functions. Alrighty, so we showed that the derivative of sine is cosine using the limit definition of the derivative. Let's do the same thing for cosine. And I told you that it's almost exactly the same, but just to kind of take my word for it, let's actually do it. So what's the definition of the derivative of cosine theta? So the limit is h goes to 0 of cosine theta plus h minus cosine theta all over h. And we're going to do exactly the same thing, except this time we're going to use the angle addition formula for cosine. So recall that cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Okay, so it's a little bit different than sine. So you got to remember that you take the cosine of both the angles you're adding first and then subtract the product of the sine of both the angles you're adding. Alrighty, so where does that get us? That gets us pretty far because this expression we're taking the limit of becomes cosine theta cosine h minus sine theta sine h minus cosine theta. So this is, of course, coming from cosine of theta plus h. And then this is all over h. And let's group again, because we have a factor of cosine theta and another factor of cosine theta. So let's group those terms together. So this is the limit as h goes to 0 of cosine theta. And then look what we're left with. This should look familiar. Cosine of h minus 1 all over h. And then now we're subtracting this middle term. So we have the limit of that. And again, I'm going to write it as sine theta times sine h over h, because we want to isolate that sine h over h because we know what the limit is. This limit, sine h over h, as h goes to 0, is going to 1. But look at this limit. This is exactly the same limit that we dealt with when taking the derivative of sine theta. The limit as h goes to 0 of cosine of h minus 1 over h is 0. I'm not going to do all the details again, but the details are exactly the same as when we took the derivative of sine theta. So the point is, this entire term is 0 because of this factor that's going to 0. Then this entire term is going to sine theta because this is going to 1. And I hope you believe that 0 minus sine theta is negative sine theta. And there it is. Alrighty, let's take the derivative of secant theta. And again, we just want to use what we know about sine and cosine. So if we take the derivative of secant theta, what are we really doing? Well, secant theta is 1 over cosine theta. So we're really taking the derivative of the quotient of the function 1 in the function cosine theta. So we can just apply the quotient rule. So the quotient rule says low d high minus high d low. So low is cosine theta. D high, derivative of 1, that's constant, so the derivative is 0. And then minus high, so 1, times d low, derivative of the bottom, but we just showed that the derivative of cosine is negative sine theta. And then all over low squared, so the bottom squared, so cosine squared theta. Okay, so this is 0 minus 1 times negative sine theta. But the minus minus becomes a plus. So this is sine theta over cosine squared theta. And we're done, but the question is just to show that the derivative is secant theta tan theta. So somehow this must be the same as secant theta tan theta. And this really isn't necessary, but it's just a little bit of trigonometric manipulation. So I'm just going to write this as 1 over cosine theta times sine theta over cosine theta. Notice that if we multiply straight across, that's how we multiply fractions, we get sine theta over cosine squared theta. And this really is, okay, 1 over cosine is secant, and then secant over, sine theta over cosine theta is tangent. So there we go. Derivative of secant theta is secant theta times tangent theta. So now that we know how to take the derivative, theoretically, of all the trig functions, we can begin taking the derivative of compound functions involving trig functions. And so let's do a couple of simple examples, and then you'll see how the idea goes. You just want to start using the differentiation rules as well as the known derivatives of the trig functions. So the key here is to recognize that this is a product of two functions. It's a product of the function x squared and the function sine x. So we need to use the product rule. So then f prime of x is the derivative of the first product, or the first function in the product, so 2x times, leave the second function alone, And then plus, you leave the first function in the product alone and then multiply by the derivative of the second function. So the derivative of sine is cosine. And there we go. Easy as that. That's the derivative. So you see we use the product rule in combination with knowing the derivatives, or the derivative of sine of x in this case. Alrighty, so we'll do one more example. Here we want to take the derivative of the function f of t equals sine squared t. And so at first, this seems a little tricky because you're kind of composing the function t squared with sine t. But the way to do this is to actually write this, well, what does sine squared t really mean? It really means sine of t times sine of t. So this is actually a product of two functions, so we want to use the product rule again. So then f prime of t, this is kind of cool how this works out. So we take the derivative of 1, of the first one, so that's going to be cosine t, and then we leave the second one alone, sine t, plus leave the first one alone, and then multiply by the derivative of the second, which is cosine t. So all in all, we get two factors of the same thing, sine t times cosine t. And there's the derivative of sine squared t. And then other examples of functions involving the trigonometric functions are similar. You just want to use those combinations of the differentiation rules and then the known facts about the derivative of trigonometric functions.